So the first thing that you end up doing in this activity, right, you're given the function f, the Dolbear function. Actually, the function's name is d. It turns the number of cricket chirps per minute, n, into the outdoor temperature in Fahrenheit, f, and it follows this algebraic formula. So if I want to know what the inverse of this function is, then what I'm really asking is to reverse the roles of input and output. And in the original function, the role of the input here is being played by the number of cricket chirps per minute. And then the role of the output of this function is the outside temperature. Right? Output is f, and the input is n. And so if I want a formula for the inverse function, what I should try to do is get the new output, the old input, by itself. Right? So solve this equation for n, which is why this problem is asking us to do that first. So I saw everyone's work on this, and it all looks good, so we'll just burn through this little part. Right? Subtract 40 from both sides. We get f minus 40 on the left. And then we get equals 1/4 n on the right. And then multiply both sides by 4 to cancel that 1/4 that's in the front. And we'll get, 4 times the quantity f minus 40 is then my expression that defines n in terms of f. And so that expression then is defining what this problem is calling the new function e of f. E of f equals 4 times the quantity f minus 40. Right? And so notice, since this equation is equivalent to the original one, all we did was we did the same thing on both sides, which we can always do to any equation, right, as long as it's reversible. It describes the same relationship between chirps and temperature, except now it does it in a way that casts n, the number of cricket chirps, as the output, because that's solved for. It's by itself, right? And f, the temperature, as the input. So it's the same relationship, it's just we've reversed the roles of input and output instead. So the thing about inverse function, right, is that it describes the same relationship between two quantities as the original function does. We've just reversed the roles of input and output. The input of the original function is the output of the inverse, and vice versa, right? That also means in particular that the domain of the original function agrees with what about the inverse? It agrees with the range of the inverse. And vice versa, the range of the original function agrees with the domain of the inverse function, because output and input have traded places. So what do you think happens if we evaluate the expression e of d of n? Okay. What I like to do with this is just think about it in a sentence first. What are we actually asking for here? E of d of n is asking the question, what is the chirp rate going to be outside when the temperature outside is the temperature given by n chirps per minute? So without even doing any algebra here, what would you expect this answer to be? If the temperature outside is currently given by a chirp rate of n chirps per minute, then how many chirps should there be outside?
E equals n.
N. There should be n chirps outside, right? Because we're just asking the same question, just in the opposite order, right? If the temperature outside is given by a chirp rate of n chirps per minute, then that must mean that the chirp rate outside at that temperature is n chirps per minute. So if we actually do out this algebra, e of d of n is e of 40 plus 1/4 n, which is 4 times 40 plus 1/4 n minus 40. And when you do out the rest of this simplification, what do you get? You just get n, as we would have expected, right? This 40 and that 40 subtract away. This 4 times 1/4 also multiplies away, and so we just get n. When we compose a function with its own inverse function, it is in fact the job of that inverse function to undo whatever the original function did. So whatever d does, e undoes. D turns chirps into temperature, and then e turns that temperature back into the same number of chirps as we started with. So j, the function which is the composition e of d, that function doesn't do anything to its input. You give that function any input, n, and it spits out that very same number as its output. J is called an identity function. It's a function that does nothing at all to its input. J of n equals n. J of x equals x. However you want to, let me make that with x's instead. J of x equals x. Identity function. The identity function is for function land what the number 1 is to multiplication land, right? It's one of these operations that does nothing to its input. It's like an invisible function, right? We can't tell when it's in there because it just is it's like a pass-through. It's like an input-output machine where you put something in the top and it just falls out the bottom unchanged, right? That's an identity function. And so we should see, anytime we have a function and its own inverse, when we compose them together, we should get an identity function. And so if we did this in the opposite direction, the same thing should happen also, right? That if I know the outside temperature and then I use E to turn that into chirps, and then D to turn that number of chirps back into the temperature, I should end up with the same temperature falling out the bottom again. So that's the test. If you want to test whether or not one function is the inverse to another, compose them together. Just stick the two machines together and see if you get an identity function out of the process. And regardless of what messy algebra happens in between, that should happen when we're composing any function with its inverse. So the way the author has used notation in this problem is also suggestive, right? What is E of D of n? Well, D of n tells me F, the outside temperature. So another way to look at this is that J of n is equal to E of F. But, on the other hand, E of F is equal to n because that's how we defined the E function in the first place. So there is a way of reading this problem, the way that the author has set up the work in the problem, to avoid doing the algebra and actually kind of, make... Written this way, it's almost what mathematicians call abstract nonsense, right? We arrive at this perfect answer, but we didn't do any sort of meaningful work along the way. It's just the way that the author set up the notation in this problem suggests how we should get directly to the answer. But again, to my point from before, I think the intent here was that you actually go through the algebraic simplification of simplifying out the composite function to see that you do, in fact, get this at the end of the day. Because otherwise, anyone could just write down D of n and E of f like this, etc., but maybe secretly this function wasn't even invertible or something. And in that case, we could write this without having to think about what the function was, but when we actually tried to do the algebraic simplification, we might hit a brick wall. So, moral of the story, the notation is set up in a way that sort of underscores that there's a shortcut here, but don't take it for granted. Do the algebraic simplification anytime, just to be sure.